welcome everyone. My name is Sonia DeBulio, and I'm the Director of Alumni Relations for the Faculty of Applied Science and Engineering. I want to thank each of you for being here with us today. I'm so delighted to see such a large turnout for today's School Lunch and Learn presentation. And today we have alumni tuning in from all over the world. We have guests joining us from 9 different countries from your registration numbers, including Canada, England, Greece, Israel, Norway, Pakistan, Singapore, United States, and Uruguay. I welcome to everyone. For those of you who are new to the Lunch and Learn, I just wanted to share a little bit of its history. The Lunch and Learn was actually founded by the class of 1935. After they graduated, it was tough times for finding a job. So the group used to meet monthly at Fran's Restaurant on College Street, and the rest is history, as they say. Well, this is a long-standing tradition that we're proud to be continuing. Before I start today's presentation, I wish to acknowledge this land on which the University of Toronto operates. For thousands of years, it has been the traditional land of the Huron-Wendat, the Seneca, and the Mississaugas of the Credit. Today, this meeting place is still home to the many Indigenous people from across Turtle Island, and we are grateful to have the opportunity to work on this land. Just a quick housekeeping item. At the end of today's presentation, we have time for a formal Q&A session. Should you have any questions for Professor Donmez, please submit them using the Q&A button at the bottom of your Zoom screen. In addition, I'd like to thank everyone who submitted questions ahead of time during the registration process. We've shared your questions with Professor Donmez before the presentation. Some of them will be addressed throughout the presentations. Throughout her presentation, while others she'll address at the end of her session as well. Now, without further ado, it gives me great pleasure to introduce our MC and chair of the School Lunch and Learn program, Lori Hevola. Lori is not only an Electrical 65 graduate, but he's also one of our most dedicated and engaged members of our alumni community. We're so blessed to have him as part of this group. Lori has been chairing the School Lunch and Learn program for several years and continues to generously dedicate his time to maintaining the Lunch and Learn long-standing traditions. And with that, I will pass it over to Lori and to welcome our speaker for today's event. Enjoy the presentation, everyone.
Thank you, Sonia, for your very warm introduction. It is my pleasure to welcome our guest speaker today, Professor Birsen Donmez, who will discuss the impact of emerging driving automation technology on driver wellness and safety. She is a professor at the University of Toronto, obviously, in the Department of Mechanical and Industrial Engineering. She is also the NSERC Canada Research Chair in Human Factors and Transportation. By way of education, she received her master's in 2004 and PhD in 2007 in industrial engineering, and also in 2007, a master's in statistics from the University of Iowa. She held a postdoctoral associate position at the Massachusetts Institute of Technology before joining us here at the University of Toronto. Her research interests are centered on understanding and improving human behavior and performance in multitask and complex situations using a wide range of analytical techniques. In particular, her research focuses on operator attention in multitasking activities, decision support under uncertainty, and human automation interaction, with primary applications in surface transportation and healthcare. Some of her honors include her Canada Research Chair Award, which was renewed for 2015 to 2025, an NSERC Discovery Accelerator Supplement in 2016, a Senior Fellowship from Massey College in 2020, the inaugural Stephanie Binder Young Professional Award from the HEFS Surface Transportation Technical Group in 2014, and an Early Researcher Award from the Ministry of Economic Development and Innovation here in Ontario for 2015 to 2020. She currently serves as the chair for Vehicle User Characteristics Committee of the Transportation Research Board of the U.S. National Academies, an associate editor for the IEEE Transactions on Human-Machine Systems, an editorial board member for Accident Analysis and Prevention, and a steering committee member of the ACM Conference on Automotive User Interfaces and Interactive Vehicular Applications. She has served as general chair for the 2018 conference. And without further ado, please join me in welcoming Professor Birsen Donmez, who will be speaking about, do smarter cars mean safer driving?
Hey, well, thank you very much, Sonia and Laurie, for the warm welcome and the introduction as well. I'm gonna share my screen, so please bear with me while I get this set up. Okay, are you able to see my slides okay?
Yes,
Maybe
we
a
can.
thumbs up? Okay, excellent. Thank you very much. And thank you everyone for joining us today. I saw some names that I recognize, some I may not know. I wish that we could do this in person so that I can meet you in person, but hopefully you'll enjoy this talk, and I'm looking forward to the discussions at the end. Let me also start my timer so that I don't overrun. Okay, so thank you again for having me as part of this event. And as it has been introduced, I'm going to talk about a question, I guess, do smarter cars mean safer driving? And I'll give you the answer to from the beginning. Partially yes, partially no, it really depends. It's a very engineering and an academic response to the questions. As it has been introduced, in my lab, we conduct research to understand human and technology interaction in complex and safety critical situations. And we do quite a bit of research about driving behavior, and more recently about higher levels of vehicle automation. In this talk, I will provide an overview of human factors research in driving with a focus on emerging vehicle technologies. And as you can tell from my title, these technologies are not always safety focused, and some of them can actually exacerbate the issues of driver distraction and drowsiness. I'll start with driver distraction in my talk, and then move to automated vehicle technologies. So some stats to motivate the study of driving behavior and traffic safety. Close to 4,000 people die every day around the world due to motor vehicle collisions. And over 90% of these crashes are attributed to driver factors. Our vehicles are highly reliable, so this number is actually not surprising. So we do not see vehicular failures, for example, come up as much as driver factors. And this over 90% number is used a lot to motivate autonomous vehicles and why we should be replacing humans from the driving task. But we will come back to that topic shortly. So we'll first talk about these driver factors which contribute to crashes. What are they? They are varied. Lack of skill is an issue. For example, novice drivers fixate their eyes less on roadway areas that are indicative of risk. So they don't know, as well as more experienced drivers, where to allocate their visual attention. So where to look for hazards, for example. Drivers may engage in risky behaviors intentionally, knowingly or unknowingly, such as texting on their cell phones. Intentional behaviors can be explained by factors such as personality, attitudes towards technology, or the behavior, as well as perceived social norms. And as impressive as human information processing abilities are, and machine vision, for example, is nowhere near capable at this stage to mimic human perception. And most of the problems that we're seeing with automated vehicle technologies today is due to perception. There are limitations to our information processing abilities. And attention is arguably the biggest limiting factor when it comes to driving. And when you look at relevant research, there is a lot of focus on what people are looking at or are not looking at in the study of traffic safety. In addition to the general limitations that we have, that we humans have, our information processing abilities may also degrade transiently or permanently. Fatigue and driving under the influence of alcohol and other drugs are major safety issues, for example. And aging is also a big concern with an increase in the older driving population, especially in the developed parts of the world. So these are all different concerns surrounding the human operator in the vehicles. We will talk about vehicle design to compensate for these limitations, but infrastructure is also very important. It can help compensate for some of our limitations as humans, but can also exacerbate some of our limitations. The images that you see here are of our instrumented vehicle, which enables us to collect on-road data. It is basically an actual car that's instrumented with cameras and other types of data collection equipment. For example, we pull data from the vehicle canvas so that we can study driver behavior and attention in the real world. We have recently conducted studies in Toronto, Canada, investigating drivers scanning failures toward vulnerable road users, such as pedestrians and cyclists. We collected vehicle and video data in addition to gaze position. So the image that you see there, my student on the driver's seat, she is wearing a head-mounted eye tracker that basically gives us data in terms of where the person is looking at or where their gaze is directed at. And vulnerable road user safety is a significant issue in our city. If you live in Toronto or are following news about Toronto, but also elsewhere in the world. So this is a problem that's near and dear to me personally and our team. Now, Toronto streets are busy with cars, streetcars, pedestrians, and cyclists, and there isn't much separation of these participants within the infrastructure, although there has been a lot that has been done recently with the COVID. So it is clear from a human factors perspective that when you do have a lot of elements in the environment that attracts or demands the attention of the human operator, that there's going to be failures happening. Here you have seen and will again see a short video from our eye tracker with a participant making a right turn at an intersection, the Bloor Street, if you're familiar. The red crosshair basically indicates the gaze position where the attention, where the foveal vision is on. And generally where you would get, so it's about 4 degrees field of view in this image where this is generally where you would get detailed information. And in this case, the participant is scanning all areas of importance for vulnerable road users. So this is actually what we would rate as a no failure case during the turn. So the person is checking for pedestrians, oncoming traffic. They actually did a very quick mirror check, over the shoulder check for cyclists as well. That's a good turn. Now, but we've also seen failure cases. So this is again on Bloor Street. And what is not clear from this image currently is that there's a bicycle lane that's to the right of the parked vehicles. So as you're approaching the intersection, if there are parked vehicles, they are blocking your view of cyclists, which requires you to do an over-the-shoulder check, basically another check for cyclists as you're making your turn. And I went all the way. And here, this driver actually fails to do that. Yeah. So we have recorded 442 such turns in downtown Toronto. And we have observed such failures, a failure basically, in about 26% of the turns. And this rate was actually worse for non-cyclist drivers. So half of our participants were cyclist drivers, meaning that they did cycle often, whereas the other half did not cycle or cycled rarely for transportation purposes. So in the failure case, the infrastructure potentially created an issue. But there can also be infrastructure-based solution to problems like these. For example, there's potential for connected vehicle technology where your car could give you a warning that you're coming to this particular type of intersection, for example, or you could redesign the intersection to draw attention of the driver to that bicycle lane that is going to merge back with vehicle traffic. Attention limits also come into play with newer technologies, just not based on infrastructure or the environmental demands. And these technologies may be built into the vehicle or they may be carried into the vehicle. This table is from Dingus et al. This is a major study that reported the largest naturalistic driving study conducted to date, meaning that they instrumented people's own vehicles and recorded data as people naturally drove, as they normally do. And this was about 3,500 drivers. It was a US-based study, but it also had a Canadian leg to it. And each driver was monitored for about 1 year. So here you're seeing data related to the technology-related distractions. You see prevalence. And so we see about, handheld cell phone use is about 6%, and in-vehicle device use is about 4% in terms of prevalence. 4% of the video clips that they basically analyzed. These are 6-second video clips that were randomly selected from the recordings. And what the data set showed in general is that visual manual distractions are the most dangerous. So when you look at relative risk, right, the dialing your cell phone increases crash risk 12 times compared to basically being attentive to the road. Talking is about twice. So anything that takes your eyes off the road is very dangerous. But what this study also showed is that drivers are not always in an attentive state. Actually, they are inattentive, you can see that they're visibly not paying attention to the road about 50% of the time. And humans can most of the time be distracted and drive well. We don't need to 100% maintain our attention on the road, except when distraction happens in an inopportune time and then a crash happens because we're not attentive at that point in time. And distraction is not always voluntary, such as when you're texting while driving, but it can be involuntary due to our inability to suppress an attention capture, such as a ringing phone in your car. But it can also be habitual. Like texting can be voluntary, but we may be reaching to our phone out of habit, probably more so now after this COVID period where we've been not really socializing, but socializing through technology. So these different reasons for distraction can inform mitigation efforts differently. Function lockouts, that is, let's say, locking out your cell phone, say on the highway after above a certain speed, may not necessarily be accepted for intentional engagement or voluntary engagement, but may be more appropriate to block habitual or involuntary distractions or interactions. In fact, there were 2 studies that tried cell phone blocker technology, and one of them was with Michigan Department of Transportation volunteers. And the results show that a lot of people overrode the blocker technology. People wanted to be connected. And there was another attempt to study teen drivers, and due to dramatic drop-off or dropout of the teen volunteers, they couldn't actually complete the study. So you can try to introduce certain countermeasures, but those also need to be accepted and used by the humans. For voluntary engagement, behavioral modification may be needed. For example, we have tested in our driving simulator parental normative feedback, basically just showing the teens where they stand in terms of their distraction engagement in a drive compared to their parent, and that has dramatically changed their behavior in following drives. Now, driving has been changing. Distraction has been studied for the past, I'd say, 2 decades at least, especially with the rise of cell phone technology. It has been a concern and is still a concern. And the need for connectivity, again, is one way that the driving has been changing. Before, it was not smartphones. You could text, but you didn't have these large screens. Now we have larger screens. But there are also smarter vehicle and traffic technologies that can help enhance driving. For example, a driver state detection system can warn drivers based on their long eyes off the road. So if they're not looking at the road for long periods of time, there could be a warning to the driver. There's also collision avoidance systems, which are really effective, that we're going to talk about. But vehicles are also becoming highly automated, and some of the implementation of automation are good, some not so good at this stage. And if you look at automation research, in particular with a human factors perspective, in other domains, process control and aviation, people talk about RNEs of automation, where you do expect that things are going to get better by introducing automation, but they don't necessarily improve performance and lead to some unintended consequences, such as over-reliance of the human operator on the automation, and when the automation fails, the human not being able to intervene and take over. Okay, so let's talk about automated vehicles. I'm not going to call them autonomous, and I know that people use them exchangeably. But really, when people say autonomous, I'm thinking about level 5 real self-driving vehicles. We don't have them. What we have is really automated technology that requires quite a bit of human supervision at this stage. So this is the famous Society of Automotive Engineers, SAE, Levels of Driving Automation Taxonomy. It is not a particularly good taxonomy, as some categories are not clear, but it's very commonly used. And when you look at the media, this is what the media uses, and even researchers uses this, so we're kind of bound by it. And I'll use this to guide my talk. So this taxonomy was created based on the level of sustained control. And level 5 at the far right is a true self-driving automation or autonomous vehicle. It will not require the human to take over driving, and it can drive the vehicle under all conditions. So this is a bit of a pipe dream, a very hard problem to solve. Even Waymo's previous CEO said that level 5 is a bit of a myth. So we'll see, most of almost maybe all of us are engineers, and we know that this is a very challenging problem that may not be feasible or, practical. Right? You may not necessarily need a vehicle that can drive autonomously under all conditions that humans can do. So what Waymo and some other companies are working on is level 4 automation. According to the taxonomy, these automated driving features will not require you to take over driving, and they can drive the vehicle under limited conditions. So examples are automated taxis or shuttles that work within a constrained geography. So Waymo has been testing this service in Phoenix, Arizona, and recently removed its safety drivers, meaning that they're operating these taxis without a driver behind the wheel. But of course, having a predefined area of operation has several advantages for the design of these technologies. And in terms of feasibility, vehicles can learn the environment. It's a smaller environment, and smart infrastructure can be built that would communicate with the vehicle also. And these vehicles can be used to support more sustainable forms of transportation. My colleagues in civil engineering talk about the last mile in transportation. How do you get to your home after you get off the bus or the subway station? And I would argue that I think this type of development is going to support our well-being more in the long run than a personally owned vehicle that's self-driving. So the top right picture is actually from the Toronto shuttle trial. And I'm working with colleagues from civil engineering on kind of trying to understand how people are going to respond to this. The shuttle is going to be operational very soon. We do have a survey out currently. So if you live around the West Rouge station area, please drop me an email so that I can send you the survey. And you might be able to also you would be able to book a ride with this shuttle and try it out. And at the bottom is the picture from a concept vehicle from JLR, Jaguar Land Rover. It has an external human-machine interface, HMI, to support interactions with pedestrians. And there was a question from in the submitted questions where I was asked whether pedestrians or other drivers could potentially kind of test the limits of these technologies or just assume that they're going to stop and then take risky behaviors. And so communicating intent through this is one way, these external HMIs is one way that risky behaviors can be prevented. Okay, now we're going to go all the way to level 0. The taxonomy says these features are limited to providing warnings and momentary assistance. They're listed as driver support features. They're also mostly safety features. Level 0 does not mean that there's no automation, by the way. When we talk about automation, it's not just control action. We can also automate, although level 0 has automation of control actions, but you could also automate, for example, information acquisition for the human, right? You can automate decision making, so it doesn't necessarily have to be the control of something. Now, these level 0 systems actually work very well. They step in when our attention is away from the road and avoid crashes. Last year, the Insurance Institute for Highway Safety released its findings for forward collision warning and autonomous emergency braking systems. So they found for trucks equipped with these systems, they found a 22% reduction in crashes. And for autonomous emergency braking systems, the reduction was 12%. So forward collision warning in trucks, 22% reduction, and AEB, 12% reduction. And back in 2016, they released a report for Volvo's city safety system and reported significant decrease for rear-end crashes also. And there were questions about insurance companies. So insurance companies are now using findings such as these to provide discounts based on safety systems that have been shown to be effective. For example, ICBC, British Columbia, offers a 10% discount for vehicles with AEB. So I Google searched that after your question, so thank you for the question. And about a decade ago, there were concerns about potential over-reliance in these systems, right? People were saying, oh, if it's gonna break for me, then I may start relying on it and not actually brake or be, more careless because the car is gonna do it for me. And it turns out that it's not a concern, right? We are seeing a reduction. People aren't depending on these systems as primary means of responding in a crash situation. They are actually doing it, which is good. Many vehicles also now come with longitudinal and or lateral control automation. And I'm sure most of you have these in your cars. Adaptive cruise control is a form of cruise control that can maintain a set time headway with a lead vehicle and slow and then speed up again. Lane keeping assist controls steering and can center the vehicle in its lane, for example. Now, if we automate either lateral or longitudinal control, SAE calls this level 1 automation. If we combine the two, SAE calls this level 2 automation. Now, these are still presented as driver support features, blue in the taxonomy as opposed to green. And these systems have to be monitored by the driver at all times. So responsibility isn't on the car, it's on the driver. However, compared to level 0, over-reliance appears to become an issue with these systems, where if you especially take both the lateral and the longitudinal vehicle control from the driver at the same time, not just one or the other. But when you're saying, okay, the vehicle is gonna steer and it's also going to do longitudinal control, you just look and monitor and step in if something goes wrong. That's actually a very hard task to do for humans, by the way. Now, a very easy perception problem for us that's detecting a huge red stop truck in our lane turns out to be a hard problem for these technologies, for what's currently available. We also, humans can also anticipate hazards based on environmental cues. It's not just perceiving the truck, but we can kind of tell how the situation is going to develop, well, at least more experienced drivers, and be proactive in our driving. Now, in this crash, which is a Tesla crash, several lead vehicles changed lanes in front of this car that crashed into the truck because of the truck that was, the fire truck that was stopped in their lane, right? I mean, as a driver who's attentive, you would think, even if you don't see the truck ahead, you would think that, well, there's something wrong, right? The traffic is going to slow down probably because all these vehicles are leaving my lane, so I'm going to do something. So what Tesla did was, rather than doing that, it actually sped up because it didn't detect any cars in front and sped up into this vehicle. Now, these technologies are far from perfect, so the driver has to be attentive at all times. And as I said, when you aren't actively controlling the vehicle, trying to maintain attention and stepping in when the vehicle fails is actually a very hard thing to do for us humans. This is called a vigilance task or a sustained attention task. And since World War II, we actually know, human factors researchers know that decrements in performance happens very quickly in these type of tasks. And they did their research with sonar operators. In about 20 minutes or so, you do actually see a stiff decline in someone's ability to be able to detect threats, basically on a sonar display. And when you do take the vehicle control and asking the driver to watch, it's a hard thing to do unless there's something really engaging in that task for the driver. And maybe because it's hard to monitor a car when we are not controlling it, the sustained attention task, or maybe because some people are over-relying on these technologies, are overconfident in what these technologies can do, we actually see misuse of these technologies with several highly publicized crashes. The Tesla system provides a warning to drivers if they take their hands off the wheel. I don't know if they've yet implemented, but now they have to implement a camera-based system after what has happened with this detection system. But basically, their driver monitoring system was that you had to keep your hands on the steering wheel. And if you took it off more than X many seconds, you would get a warning. And if you're getting the warning recurrently, then the car is going to shut down. But people were tricking the system, right? They were stucking an orange. And I think there are even kind of aftermarket technologies being sold to trick the sensors into thinking that the hands are on the steering wheel. And we have seen real world events, as well as in research studies, that people engage in distractions improperly with this type of automation. But of course, when people aren't engaged in a distraction, if you're just watching and being attentive when it's not an engaging task, then boredom would set in and potentially drowsiness and sleep would set in, arguably even more dangerous than distraction when it comes to driving, because it's a state that you cannot come out very easily. Distraction, within a few seconds, you should be able to get your attention back on the road. If you're sleepy, there's sleep inertia. If you're falling asleep, it's going to be in the order of minutes rather than seconds, probably. Even if you kind of get startled into responding, your response isn't going to be as good as when you're not sleepy. Now, distraction and drowsiness are two big issues that the driving safety community has been dealing with before these level 2 systems, and they're not going anywhere. And the risks are also not uniform across different driver groups, which makes the issue more complex to deal with. What we're seeing, for example, I'm talking about Tesla because Tesla has Tesla is kind of presenting the technology as, let's say, full self-driving, quote unquote, but you're still responsible. And they're also allowing their drivers to use it in, let's say, out of the highway situations where it's not as capable, and doing testing. Whereas, other vehicle manufacturers have similar technologies, but they're kind of presenting them or providing them as more driver support features. So Tesla gets a bit more criticism from me, and I think researchers like me for these reasons. Now, we have conducted a driving simulator study with 64 participants. And the image that you saw on the left is our driving simulator. And we gave them so half of the drivers were novices, half of them were experienced drivers. We gave them a secondary task, we call it's a visual manual task, kind of scrolling through a list of songs. It's in a controlled manner. It was self-paced, so they were deciding when to engage and how much to do that. And it was on that display that's highlighted with the red box. And then we looked at, how much people were taking their eyes off the road using the same eye tracking technology, the red crosshairs that I showed you earlier. So this is non-automated driving or manual control. You're looking at duration of off-road glances. So when you take your eyes off the road, how long you're looking away. And so overall, experienced drivers were taking their eyes off the road for shorter periods of time, and they would actually look away more frequently, but would have less long glances. And this is in line with previous literature for driving and driver distraction. So switching to, but in general, when you look at the duration of glances, this is average. It's less than about 2 seconds. 2 seconds is generally used as a threshold. Like about 2 seconds, real-world driving data has shown that your risk of a crash actually doubles. So if you take your eyes off the road more than 2 seconds, that's double the crash risk. Now, when you move to the automated version, this is level 2. So we had them give up both lateral and longitudinal control, but ask them to monitor the vehicle. And in a practice drive, they've actually seen a case where the vehicle couldn't handle something, so they knew that it had to be monitored. So switching to level 2, we saw this gap widen between novice and experienced drivers, with novice drivers engaging in the task more in general. But of course, so those were the means. So these are box plots. I hope that you remember from your stats courses, but it's based on average for each participant, basically, and then you see the distribution. But when it comes to safety, extremes are more relevant than the mean. So we've recently reanalyzed this data with a quantile regression. So the plots that you're seeing, again, for novice and experienced drivers, non-automated and automated. And it shows the individual driver glance distributions. So this is akin to a PDF. The individual distributions in gray, their combined glance distribution in blue. And the 3 red vertical lines are the 15th, 50th and 85th percentile glance durations, right? We are really concerned about the 85th percentile, the really long glances that each individual has. So on the average, when you look at where that falls, for novices, you're already with manual driving, you're already about 2 seconds. Once it switches to automation, it goes to 5 seconds. And you don't see as much of a shift for experienced drivers. Okay. And aside from driving experience, improper engagement in non-driving activities or distractions while using these technologies may be in part due to people not understanding the capabilities of technology. We recently completed an online survey with over 400 drivers, asking people about their knowledge of adaptive cruise control, ACC, and lane keeping assist, LKA systems. The table shows some of the general limitations we have asked about. We have asked more. But the statements that you see there should be all no. So ACC has full braking power, no. So people shouldn't have agreed to that. Does not have difficulty on curvy roads, it does have. So basically these are some limitations that people shouldn't have agreed. So that's the first column of percentages should have been 0 ideally, right? Oh, sorry. Percent of people who agreed. Sorry, these numbers should have been 0. People shouldn't have been agreed. So the first column is for owners, people who said that they own 1 or 2 of these systems, and then the other one is people who do not own. So we see around about 50% of the respondents incorrectly agreeing to a majority of these statements. Now, and owners did not have better knowledge than non-owners, but had a stronger bias in favor of system capabilities. On the right, you're seeing the receiver operating characteristic curves. And basically, it does show very low levels of sensitivity, almost on the diagonal, just guessing. And we further found that worse understanding of these systems is associated with higher trust, self-reported higher trust, which in turn is associated with greater intention to engage in non-driving tasks with these systems on. I have a PhD student who is looking at training, testing different training options basically for this. So one way to address over-reliance is through training. And she's basically has one version of training, which is based on focusing on limitations found in an owner's manual, but there are several. And then the one on the right is more about focusing on the driver role while using these systems. And interestingly, version B is as good as version A, maybe even better. So it may not be feasible to teach everyone. And when you look at the driver population, there's really varied backgrounds and technology savviness that they may or may not understand all the limitations of these technologies. So teaching the drivers their responsibility and that these systems may fail may be what needs to be done. Now, there is also more than ever a need for driver monitoring systems to be implemented in vehicles, both for distraction, but also for drowsiness. The National Traffic Safety Board, Transportation Safety Board, basically released recommendations last year for these systems. They've done, so normally NTSB does investigations for transportation, but major transportation crashes. So they would do aviation, and then they might do, train derailments, etc. So they know, or they might do, semi trucks, but they wouldn't do passenger vehicle investigations. It's just with Tesla crashes coming up, NTSB was pulled in because of these automated systems being introduced into these vehicles. And NTSB released several recommendations, and one of them is to basically create driver monitoring systems. And European Union is ahead as they plan to make driver monitoring systems mandatory in all new vehicles by 2022. We'll see what kind of driver monitoring systems we'll get, but it is in the right direction. And with the with kind of the political changes in the US, we're also seeing that there's going to be more regulation when it comes to these type of technologies. Now, we have not yet seen good implementations of these driver monitoring systems that have been implemented in commercially available vehicles already. And different types of sensors have different issues associated with them. There are implementations of systems based on vehicle measures, such as steering wheel inputs. You might have seen, you might have a car that would show you a cup of coffee, when based on you maybe driving just extended periods of time or not moving your steering wheel much. Now, when you come to level 2 vehicles, we talked about Tesla has that hand-on wheel detection. GM has Super Cruise, which is another level 2 system like Tesla, but it's only functional on highway in highway environments. It does use a driver-facing infrared camera, but when there's direct sunlight, then the infrared camera kind of loses the tracking, and then Super Cruise basically deactivates. And same with when people are using certain types of sunglasses. But also there are privacy issues when it comes to monitoring, especially if it's a camera recording. And then there are equity issues also with detection and facial recognition. These systems may work better for certain facial features, etc., and may not for others. So in my laboratory, we explored use of physiological sensors in addition to camera-based systems, basically to augment these existing technologies. But overall, more work needs to be done in this area. It is hopefully it's going to come. I think it's going to be a very useful technology. It's not like vehicle control automation. Even if it fails at times, it's okay, as long as it can detect these high-risk situations when you're falling asleep or when you're distracted for extended periods of time. It would be very valuable. Again, with drivers not depending on it as the primary means of determining when they are impaired. Okay, I have 5 more minutes. I'm almost done. I have, I think, 2 more slides. So you may be wondering what's happening with the level 3. We didn't talk about that. So these systems are called to be automated driving systems, in that they would not require driver monitoring of the system, but the driver must take over and drive when the system requests. So there's a request from the system, and there's a need for driver takeover. So one can imagine the sheer terror if it happens in an emergency situation, that you weren't paying attention and you weren't required to, and you were talking to someone, or you were watching a movie, and all of a sudden there's an emergency situation and you get a takeover request and you have to do something about it. So there are safety and also regulatory concerns surrounding this level. So we don't have any such systems currently on the roads, as far as I know. I know that several manufacturers were planning. I've recently read that Hyundai is going to implement something. I don't know if they have or not. But I think what the manufacturers are talking about is traffic jam assist, basically. So in low speed conditions in traffic, where you can give the control to the car and then you can do something else, hopefully not sleep, because if you come out of sleep, we know that it can take about 15 minutes for you to get back to good performance again, right? There's sleep inertia that you may not be able to get rid of. Okay. And the idea of level 3 systems has generated the concept of takeover requests, or TORs, the system detecting a need for driver takeover and then alerting the driver to do so. One can imagine these takeovers to be scheduled and ahead of time, right, approaching my exit, and then 5 minutes ahead, I get a takeover request, and then I have enough time, and it's not under emergency situations I do this. Or it could be an emergency situation, example, automation losing lane markings or some sort of a sensor failure. and doing this request. I'm saying assume because these don't exist. People are testing it in simulators and seeing how drivers are reacting, how many seconds do you need, etc., but nothing has been implemented. Now we have explored takeover requests for level 2 vehicles where the driver has to monitor the car and the road, and found that although people performed well during takeover scenarios where they had to step in, they showed a tendency to over-rely in this and not pay as much attention to the car and the road, thinking that there will be a takeover request. So there was an over-reliance problem. But adding basically traffic information in addition to takeover requests rectified that issue. And this, I think, goes back to keeping the driver engaged in some way in the driving task or the monitoring task. Okay, so thank you very much. I hope that it did make sense. So I'd like to conclude by saying that there are significant advances, but also much hype in vehicle technologies in terms of their capabilities. They're all commonly inflated, especially in media. Level 0 systems which have properly considered human factors issues perform very well, actually. The road to full automation is long and according to some, non-existent. But as these technologies are advancing and being tested, there needs to be more oversight protecting public interests. Thank you.
Thank you, Birsen. We are running close to the top of the hour, but we have had a number of questions posed in the chat. I'm going to begin with them in no particular order. The last question is rather interesting. Do you believe that Tesla can eventually achieve a true level 5 automation level?
I would say that I don't know if when level 5 would be achieved, because when we say level 5, it's claiming that it can drive under all conditions. You take it to a rural part of Turkey where I'm actually currently at, where there may not be lane markings and it's going to be able to drive, right? So, first of all, that may not be feasible, but let's say in the US or Canadian roads, will it achieve? I don't know if it would be able to with what it's currently doing. There seems to be a lot of edge cases. They're promising a lot. It's not getting there. And it may not be the best approach. So you also see these other companies that entirely skipped what Tesla is doing and moved to level 4, right? Google, for example, they thought that trying to go through these level 2, level 3 is just dangerous. So you might as well just have self-driving, but not depend on the human driver as you're doing that.
Thank you. The next question, have there been any tests regarding camera-related blockages for LKA? That is, salt buildup on the camera during the winter periods, which obviously here in Canada is a big issue.
Yes, I don't know, but obviously if it's not detecting lane markings, there would be an indicator, right? If you have an LKA system, it does actually kind of draw the lane markings when it's detecting it. I don't know how salt buildup affects it and how long you need that, how long you shouldn't be washing your car to get to a level where it's going to degrade the sensors. That I don't know, but I do assume that if the sensors aren't detecting the lanes, that information would be presented to the driver in a reliable fashion. But I don't know the tests.
Thank you. Are there studies looking at the reliance on forward crash detection and AEB for drivers who never experienced driving without these systems?
Never experienced driving without these systems. That would be a very small subset on young drivers probably, right? Because these systems are still relatively new. I don't believe so. There has been quite a bit of research before these systems became widely available in simulators, etc. And as I said, there was over-reliance considerations, but there seems to be a reduction so far. So I guess we'll see what happens if you end up driving a car that doesn't have these systems. I don't know.
Next question has to do with cell phone connectivity. How are you able to collect the data on cell phone use by drivers?
So there are various ways of doing that. When we do research, we can do surveys. For example, we do create conditions in the simulator. That naturalistic study that I talked about, the large study with 3,000 drivers, they had cameras looking inside the vehicle. So they had people coding manually when the driver was interacting with a cell phone. So that's another way of assessing that. And when crashes happen, at times, people would access basically cell phone use records of the driver and will get that type of information.
Okay, I've just got a message. One last question, and this is a morality question. What if the vehicle loses control and you are the only occupant? Under those circumstances, will the vehicle crash into a pole or stop instead of killing or maiming 5 people standing on the corner of perhaps a T intersection where the vehicle went straight instead of turning?
Yeah, so this is an interesting question. There's this thing called the trolley problem that I think you may have seen, which is used in the psychology studies to understand kind of human morality and decision making. So I've heard this question asked to Chris Armstrong, who was the lead in Google Car, right? Now Waymo, and who is now leading Aurora. And he didn't really see this as an issue, I think, that they're dealing with. He did say that they would design the car that it wouldn't put itself in a situation like that. So I think I want to first say that. And then secondly, I've also read a little bit more about this, and I know that there was a submitted question. And I think if we can assume that the car knows really the situation that well, that the car wouldn't put you in that situation. If the car has put you in that situation, it wouldn't know that there are 5 pedestrians and there is a pole. So I think there's also the technicalities that this might be, like at this stage in design, maybe these type of questions really are far away in the future, that technology has to be developed a lot more before we have to worry about these kind of situations where you're in an emergency and you have to make a decision.
Good. One last question to do with computer coding. What are the challenges for coding for roads that are designed relatively poorly in layout or signage, say for us here in Toronto, compared to more modern layouts, designs and signage like in Phoenix or Las Vegas?
Sorry, could you repeat the first part of the question? What are the coding challenges?
The coding challenges for dealing with the road network here in Toronto, which is relatively poor compared to a more modern city, these are my words, such as Las Vegas or Phoenix.
Yeah, of course. I mean, there's a reason why Waymo started in Phoenix, right? Even in the US, where the lanes are really wide, there isn't as much pedestrian traffic, and everything is nicely marked, and weather is always nice. So absolutely, right? Once the infrastructure gets less defined, less well-defined, the rules of the road get less well-defined, the weather gets worse, it makes it a more challenging engineering problem to be able to build perception into these vehicles.
Right. Well, on that note, since we are a few minutes past the hour, first of all, I would like to thank the audience for all of their questions, both when registering for the event and especially during the Q&A. Obviously, I want to thank Professor Donmez for being with us today. Thank you for such an informative and entertaining presentation on driving automation technology. To everyone who joined us here today, we invite you to provide your feedback on the School and Lunch and Learn series. Shortly, you will receive a link to an online survey. It was made available in the chat and will be shared with you by email after this event. Also, a link to the presentation, which was recorded today, will also be shared with all registered guests early next week. Traditionally, School Lunch and Learn events are held on the second Wednesday of each month. However, for the month of December, it will be on the first Monday, being Wednesday, December 1st. The guest speaker will be Professor Mark Korchek. And again, he's got an interesting title for his presentation, Something from Nothing, the Practice and Promise of 3D Printing. For more information about our next School and Lunch and Learn presentation, please visit the engineering website. In closing, we would like to again acknowledge and thank MBNA, the sponsor of School Lunch and Learn through U of T's Pillar Sponsorship Program. If you are interested in learning more about the School Lunch and Learn, please contact the alumni office at events@engineering.utoronto.ca. In closing, I would like to thank all of you for joining us today for another great presentation. And I hereby adjourn today's session of School Lunch and Learn. Have a safe and wonderful rest of the day. And we hope to see you on Wednesday, December 1st. Thank you.